Hi everyone, so here we are in our next week of remote learning, and in my basement again over here, and I'm going to be giving you guys the notes for Unit 8. We're going to bypass Unit 7. I just don't have enough equipment in my house to really be able to teach you guys that unit very well. So we're going to go into Unit 8, which is on wave, sound, and light, and I've divided this unit up into 3 little pieces, so there's 3 separate videos. This is the first one on waves. Next one will be on sound, and the one after that is going to be on light. And this is kind of the next unit that I was planning on teaching you guys, but since we're obviously not in school, this is kind of where we are. After we go through all these notes, your assignment is actually just take the notes and show me that you actually did. Just send me some pictures of it, and then from there we'll probably go on to nuclear physics, and it might round out the year there. So this week is all the notes. The next couple weeks are going to be a couple of virtual labs kind of delving into the topics that go into this entire unit. This is actually a unit that's got a lot of different kind of applications throughout the world, throughout the universe. So definitely be bringing some of that in. So here we go. So this first part is on waves. And this was actually, if you remember, way back when to the reach performance task. It was on waves. So here we go. Unfortunately, the reach performance task, oh, they're not there anymore. Oh, too bad. So you want to think of a wave as a wiggle in time. And I'll just note that these slides, I'm going to post them online also on Google Classroom, all as one giant file. All 3 parts together. So if you don't want to start and stop the YouTube video, you can have the notes open with you, the actual slides open with you, and then just follow along. Oh, so a wave is a wiggle in time. There's some sort of disturbance, there's some sort of thing that is traveling through some sort of medium. If you ever look at waves on an ocean, that's what this picture is here, where the waves on the ocean are actually created by the wind blowing across the surface of the water, actually pulling the top layer of water along. And the more wind, the faster the wind speed, the more water is actually being pulled along. So when we say don't think of a wave as a physical object, that's a huge misconception. A wave isn't anything. I can't take a wave and put it on a scale. That doesn't work. What you can do is you can take a wave and actually send it through something. So it needs some sort of medium generally to travel in. There's an exception to that case. But there's some sort of energy that is moving through an object. And that is what a wave really is. There's some sort of energy, there's some sort of disturbance that is moving through something that is causing either some molecules or some energy to go under some sort of oscillation. When we talk about an oscillation, it's some motion that is actually going back and forth, back and forth, back and forth. So there's 2 types of waves. The first is this transverse wave. And definition is the vibration travels perpendicular the direction that the wave travels in. And I can see you're getting a little bit of the flickering on the screen there. I apologize for that. The flickering is because the frame rate of my video camera versus the frame rate of my TV, there is a slight offset of the 2. And that's why you can see the flickering on the screen. So in this case, this is your transverse wave. It's a sine wave, or cosine wave depending on where you start from trigonometry. The wave is going up and down. The vibration is traveling up and down, but the wave is propagating horizontally. A good way to think of it is, let's use this, some Charmin that everyone is trying very desperately to find. So if I stretch out a length of the toilet paper, I'm going to do a transverse wave. I'm going to flick the end of it. And if you notice that I flick the end of it, my hand only moves up and down, but the wave appears to be traveling across the length of the toilet paper. This is the hallmark of a transverse wave. The vibration goes one direction, but the wave travels, or we say it propagates, in another direction. So I'm moving my hand vertically, and the wave is actually moving horizontally. Let me roll this up because this might be needed later on. So there's a couple terms that we're going to talk about with this. The first one is what's called the amplitude. The amplitude is the height of the wave. So this horizontal line here, think of this as like a baseline or an equilibrium point. It's sort of the middle point of the wave itself. And the amplitude is from this equilibrium line up or from the equilibrium point down. A good way to think of amplitude is, for a sound wave, it's the volume. The louder the wave, the higher the amplitude is. For light, the brighter the light, the higher the amplitude is. This case, you can think from the equilibrium point up as a positive amplitude, or from the equilibrium point down as the negative amplitude. The peak of the wave is what's called the crest. If you ever go on any sort of boating exercise or out on Lake Michigan, they'll often talk about the marine forecast, and they're telling you about the wave crests. They're saying from the base point of the lake how high the waves are. Bottom part is called the trough. So going back to amplitude, amplitude is either from the equilibrium point up to the crest or from the equilibrium point down to the trough. The next one is wavelength. So wavelength is one complete section of the wave. So if I start at this point where the wave crosses the equilibrium point, you go up through a crest, down through a trough, and back again. That is one complete wavelength. This entire wave picture has two wavelengths to it. So you have one and then two. It can be drawn anywhere. I like to draw it along the baseline, along the equilibrium line, but it often can be drawn from crest to crest as one wavelength, so this entire section would be one wavelength, or from trough to trough. So from here to here would be one entire wavelength. That's really more or less his personal preference. The other type of wave is what's called a longitudinal wave. And yeah, I drew this. And this is not a smart board. It is sharp, because that's the name of the TV. It is sharp here, but it is not very smart. So, longitudinal wave. Back to the toilet paper. So, transverse wave, I did this. And the wave kind of propagated along the length of the toilet paper. So I flicked the wave up, I had the vibration go upwards, and the wave propagated horizontally. This is going to be a longitudinal wave. So watch the direction of my hand now. I go in the same direction that the toilet paper is moving in. This is a longitudinal wave. What happens is the wave propagates in the same direction that the vibration happens in. So here in transverse, they're perpendicular, and longitudinal, they're parallel to one another. This is like a compression wave. If you've ever been stuck on traffic because, well, the school never really moved, going down to 14th Street at Medill, you would see that sometimes the cars will all just bunch up together, and also you're driving, and for no apparent reason, like traffic, it just eases up. You can go at 50 miles an hour down the expressway. Traffic has been thought of as a longitudinal wave. You have sections that are compressed, or we call them a compression. So if you think of this as like a slinky, those spring things that go down the stairs. If you think of it like that, this is where all the particles are kind of pushed together. And when they get pulled apart, you go what's called the rarefaction. And the rarefaction is this entire section right here. So here's a rarefaction, here's another one, here's another one, here's another one. The compressions are where all the little loops are really kind of pushed very, very tightly towards one another. This is what we're going to talk about when we talk about sound in the next part of the lesson, in the next part of this unit. And now for wavelengths. Well, there's no sort of like up and down, so where's the wavelength? Well, the wavelength is thought of from compression to compression. You could go from rarefaction to rarefaction, but I find it harder to find the centers of it. The compressions, well, they are small enough, because they are compressed. So I go 1, 2, 3, 4 wavelengths in this entire span here. Now those are the two types of waves, the transverse and the longitudinal. Now we want to take wavelength and add time into that mix. So we talk about frequency. So frequency is the number of wavelengths per second. It's also measured in hertz. So hertz is cycles per second. So for example, if you ever tune a radio, the numbers of the radio station are not some random numbers. Those numbers are the actual frequencies of the radio waves that radio station is emitting. So for example, KISS FM 103.5, that radio station is emitting a radio wave of a frequency of 103.5 megahertz, or millions of hertz. So if you look at two waves here, so here's two examples. Let's look at this first one. Let's count the wavelengths. You go 1, 2, 3, 4, 5, 6. There's 6 wavelengths here. Let's look at this guy here. We've got 1, 2. So we've got 6 wavelengths, 2 wavelengths. Now if we add time into it, let's say each one of these waves actually lasts 1 whole second. So in this first wave we have 6 wavelengths in 1 second. So we get a frequency of 6 hertz. This one we have 2 wavelengths in the same 1 second time span. So we get a frequency of 2 hertz. So for example, those of you who are musically inclined, middle C on the piano has a frequency of 256 hertz. That means that in 1 second, 256 wavelengths go past you. If you ever went to an orchestra concert and everyone tunes to what's called concert A, it's 440 hertz. If you can read sheet music, it's the 3rd space in the treble clef. And the reason why they picked that one is because that's one of the few notes that every instrument in an orchestra can actually hit. And when they play that, that is at 440 hertz. So if you were somehow able to see these waves of the orchestra, you would see 440 wavelengths going at you every single second. So let's look at some of the problem here. So this would be like what we'd be doing in the little orange folders that I have in class. So in this picture here, and this is where probably having the PowerPoint, looking at it would be actually pretty useful. So this entire wave lasts 2 seconds. Say, what is the frequency? Well, frequency is number of wavelengths per second. So you have to see how many wavelengths. So I have 1, 2, 3, 4. So frequency, I have 2 wavelengths in 2 seconds. So I have a frequency of 2 hertz. But what is the wavelength? Well, if there's 4 wavelengths, this is one little wavelength here. So in 10 meters, I have 4 wavelengths. So the wavelength of this entire wave is 2.5 meters. In the next picture, so we have this wave here. It lasts 3 seconds and it's a total length of 7 meters. So see, how many wavelengths are there? Well, let's count them. 1, 2. So there's 2 wavelengths. Well, what is the wavelength? Give me the something meters of it. Well, if I know in 7 meters, so the 7 meters, there's 2 wavelengths. 7 divided by 2 is 3.5 meters. Now, what is the frequency? So if this wave is 3 seconds, and I have 2 wavelengths on that, again, going back to the definition of wavelength, of frequency, sorry. Frequency is number of wavelengths per second. So I have 2 wavelengths in 3 seconds, which gives me a frequency of 0.67 hertz. This bottom piece here, this is an example of a radio station. This is a 107.9, which is a La Ley on the FM radio station. and it's 107.9 megahertz. And so that means that the waves coming out of the transmitter tower, you're getting 107,900,000 wavelengths every single second. This is FM. FM is in megahertz. AM is in kilohertz. So the radio station 670, which is I think the score AM, that's 670 kilohertz. So that is 670,000 hertz. So let's look at what is actually represented by each wave. So that's fine, we've got these waves, but so what? What's actually represented by them? Well, a transverse wave does not need any material to travel in. I mean, what we mean by material is either air, water, some sort of object. No physical object has to actually vibrate. And the reason why is because a transverse wave, all these guys are what are called electromagnetic waves. So if you think back to electric fields, when we did the balloons and the rubbing with the fur, that created an electric field. Well, if you have an electric field and a magnetic field, which, sorry, we didn't talk about magnetism, at the exact same time, what happens then is, and if you start oscillating it, so imagine you take the balloon, rub it with fur, and you start shaking it. You have a magnetic field, you have an electric field just because you have the charges in the balloon. But the fact that you are moving it creates a magnetic field. And those don't need any material to travel in. So light is a transverse wave. Well, duh, because there's no air in space. So light's got to get from the sun to us somehow. TV, radio, cell phone waves, those are all transverse waves. Even if you have a dish, that's a transverse wave. I'm not talking about cable, like TV, like an antenna or a dish. Like if you have the actual cable, that's something totally different. Microwaves, that's an example of a type of a wave. What's really cool, you actually, if you have a stick of butter and you put it in a microwave, and you actually don't put the turntable on, you just put the stick of butter centered in the microwave, and you set it for maybe about 30 seconds or so. You're going to see in the stick of butter, you're going to see two little divots in the stick of butter itself. Those are two of the crusts. Those are the crusts. Those are where where the wave actually crosses that equilibrium point. You can see that in the stick of butter. X-rays, that's another type of a wave. And that's why X-rays are so powerful when they're trying to actually do some sort of like dental procedure or trying to look at your bones. And because X-rays can travel through your body, that's why the dentist, often what he does is he puts this lead bib over you, and for the guys it goes a little bit lower, they go off the screen and say, don't move, and then they come back and say, oh look, oh you have cavities. A longitudinal wave, this needs something to travel in. And this, for our studies, is going to be sound. This is the topic of the entire next part of this unit. We'll talk more about sound then. But sound needs something, some sort of material to actually travel into. So with this, let's look at this, how we find how fast a wave is going. So when we think about how fast a wave is going, if we go back to our Charmin here, it's not this part, it's not my hand going up. It is how fast, if you follow the kind of like the hill being created from my hand to the roll, it is how fast that little hump is actually moving through the piece of the toilet paper. That's what we're doing here. So the wave speed is equal to the frequency of the wave times the wavelength. We think back to what we did sometime probably in September, the very start of the school year. We talked about velocity as distance over time. The same equation. Wavelength is the distance, frequency is the timepiece. But since frequency is 1 over time, we have distance over time here. So velocity, basic, is meters per second. Frequency is measured in hertz, which is Hz. And wavelength, it's the Greek letter lambda. So it kind of looks like an upside down Y. It's a lowercase Greek letter L, whereas this wavelength is in meters. Just to give you guys an example, the speed of sound, so the sound that you're actually hearing coming out of whatever sort of apparatus you're using, is coming at you at roughly 330 meters per second. The speed of light, so the light leaving whatever sort of apparatus you're using and going to your eyes, is going at 300 million meters per second. And more of that to come in an upcoming lesson. The other thing we can talk about is the period of the wave. So wavelength was kind of how far in distance one complete cycle is. Period is how much time it takes the wave to go through this one full cycle here. So a good example is the Sears Tower, or Willis Tower, or I think it got sold to somebody else. So the Sears Tower has been recorded to sway back and forth about once every 10 seconds. And it sways back and forth about 3 meters or so, or it could be 3 feet. I don't want to, but it sways back and forth. And if you're at the observation deck on a really windy day, you can stand there, you can actually feel like the building literally moving. It's designed to do that. It's not like, oh my god, it's actually going to break. No. There's a legit reason for that. It's actually doing that to help actually prevent excess stress and strain in the building from the winds that are, at 1,000 feet up. So when it swings back and forth 3 feet, it goes from its center point out 3 feet, back to the center point, out another 3 feet, back to the center point. And it takes about 10 seconds for it to do that actual sway. At 10 seconds for it to do one complete rotation, that's what we call the wave period. How we calculate the wave period is the wave period is 1 divided by the frequency, or T is equal to 1 over F, where T is the period of the wave in seconds, and F is the frequency of the wave in hertz. And what I'm doing is I'm kind of going a little bit faster here than I normally would in class, just to make the video shorter. But I'm sure, feel free to pause and stop it as you go through, and then follow along with the online PowerPoint. So let's look at a couple of problems here. These equations are pretty basic. We've done them before. It's like Newton's second law. It's like when we talk about work. It's like when we talk about Ohm's law. You're multiplying two things together. So here's a couple of examples. So you calculate the speed of waves in a puddle that are 0.15 meters apart. That means how far apart the waves are. That's your wavelength. You're tapping the water twice each second. So you're going, every second you're going 1, 2, 1, 2, 1, 2, 1, 2. That's the frequency of 2 hertz. So the velocity is the frequency times the wavelength, so 2 hertz times 0.15 meters, you get 0.3 meters per second. Next one, very similar. This one just tells you straight up what is the speed of a wave in a water that has a wavelength of 0.4 and a frequency of 2 hertz. We just multiply the two together. Number 3 is what is the wavelength produced by a 256 hertz tuning fork. This is, the tuning fork is a device used to tune things. And that's actually middle C, where the sound travels at 1500 meters per second. So here you're trying to find the wavelength. So you're trying to solve for lambda, so you divide both sides by frequency. Frequency is, wavelength is velocity over frequency. So you get wavelength is 5.86 meters. This next set of problems is what happens if we're talking about wave period. So what is the period of a wave of frequency of 512 hertz? So that's the only number you have, and that's the only number you need. So the period is 1 over the frequency. So you get 1 over 512 hertz. The thing with these problems is you're going to end up carrying a lot of decimal places. Because if you're at round this number, 0.0019 seconds, to our normal 2 decimal places, you're gonna get 0. So you take it all the way out to 4 decimal places. My rule for doing problems like this is you want to take your answers all the way out past the first 2 non-zero numbers. That's where you'd like to go. Otherwise you might have to go a little bit farther, or just put it in scientific notation. So everything we've done so far is what happens when we have a single wave happening. Well, now we say, well, what happens if we have more than one? Which is legit like real life. There's more than one wave going on here. So we do what's called a wave superposition. This can be for light or for sound. Those are the two that we're going to talk about the most. And if you think of wave superposition, you're taking 2 waves and they're overlapping on each other. And when they overlap on each other, you don't see the first wave, you don't see the second wave, but you see what kind of is left over, or the combination of the two. There's a lot of really good applications for wave superposition. If you're musically inclined, if you ever play a chord, so either on a piano, major chords on a piano or 3 notes, on a guitar you're strumming multiple strings, but it sort of sounds like one really nice sound, that is wave superposition. You're overlapping multiple notes together to create one very nice sound. The first type of wave superposition is what's called constructive interference. So here we have what are called 2 waves. So here is wave 1, wave 2, and we say they're in phase. So if I were to move with both these waves forward, both waves hit the crest at the same point, both waves hit the equilibrium line at the same point, both waves hit the trough at the same point, and back to the equilibrium line. They're kind of like doing like, they're swimming together, It's like synchronized swimming. They're both going together at the same point. What happens is when these 2 waves, when they overlap into one another, you get a single wave that has, this is perfect constructive interference, has the same wavelength. So this wavelength is the same as this one, is the same as this one, but look at the amplitude here. This is now almost twice the size. So it's this amplitude plus this amplitude gives you this one together. So what happens is you get some louder wave that happens here. A very good example, this is an old school phone. This phone, not a cell phone. You actually had to like stand by the wall with it. Ay Dios mío. But if you even use your cell phone now, and you have the sound on, and you press the different buttons, the keypad has 12 buttons to it. However, it's actually 12 buttons, but it's only 7 sounds. It's 1 sound for the columns, and 1 sound for each row. So if I dial number 4, I'm hearing the beep you hear is actually 1209 hertz plus a 770 hertz sound. And just don't add up the numbers and go, oh, it's whatever it is. No, it's something kind of in between the two. There was somewhere I saw where you can actually play Happy Birthday to someone by pressing a different set of buttons. I don't know what that one is. So if you've ever gone to, let's say, a movie theater, or you're setting up, you get one of these crazy home theater systems, and it's all little speakers that you set up all over the place, and they always tell you, aim the speakers at the center, wherever someone is going to sit, so at the sofa. Why? Because you're trying to maximize this. You're trying to maximize constructive interference. Because when you have multiple speakers around you, all the sound waves are propagating throughout the entire room, and you're going to end up with dead spots. And what are the dead spots? The dead spots are destructive interference. This is where the sound waves are overlapping on one another and they are perfectly canceling each other out. And when you're setting up a theater system, you like to avoid that. Because if you have dead spots in your home theater system, nobody's going to want to come and watch movies with you, and you're not going to have a lot of friends. So this is destructive interference. the two waves, they're out of phase. So what does that mean? This first wave goes up to a crest, while this bottom wave goes to a trough. So one wave is cresting, the other one is troughing. So they're totally opposite of one another. So you have a positive amplitude here, a negative amplitude here. This is, let's say, positive 2, this is negative 2, positive 2, negative 2, you get 0. And they totally cancel each other out. Remember how normally I show a lot of the videos in class? Well, if you go into the YouTube channel, my YouTube channel, you'll see a bunch of videos in there called Unit 8. And one of them is on noise canceling headphones. Go watch that one, because what noise canceling headphones do is they do this. They do this constructive interference. So there's some outside noise that you're trying to basically cue out. Now what the noise canceling headphone does is creates a sound in the headphone that is the wave that it's trying to get rid of, but it takes that wave and actually flips it over. So you have the wave that's trying to get to your ear, and then your noise canceling headphone takes that wave, says, oh wait, let me spit out a wave that's opposite of it. The two are going opposite of one another, and what do? They cancel each other out. Acura, a number of years ago, actually did that in their cars. They actually had sensors and microphones in their cars that actually would send out opposing sound waves into their actual engine compartments to block out unwanted engine noise, so your car is inside where you're sitting is nice and quiet. Now, what we've talked about so far is basically constructive or destructive interference, where it's either all or nothing. It's either all constructive or all destructive. But what happens if you get kind of a mix of the two? If you get a mix of the two, you get what's called a beat pattern. And this is where folks that play musical instruments, especially string instruments, talented musicians, this is where they have a very good ear for music. If you know someone who's really good at playing a string instrument, and they can really tell, an A from an A flat or a B from a B flat. They have a very good ear for music. And what they're listening to is what's called a beat pattern. And in a beat pattern, you have two waves that are very close in frequency to one another, generally 5 to 10 hertz apart from one another. And what happens is when you overlap them, you don't hear one note like a, you hear a sound that is pulsating like a, that's what you hear. Because what's happening is these two waves are undergoing alternating perfectly constructive interference to perfectly destructive interference. But when they're between the two, it's a combination. Think like the roller coaster example. It's either all kinetic energy, all potential energy, or a mix of the two. So you have two waves here. This is a 40 hertz wave and a 50 hertz wave. When they overlap them, if you notice these two waves, the amplitude is all the same. But when these two, the amplitude kind of goes up and down, up and down. We call this, if I come on this side, hello, here I am. If you look at this, so we call this the envelope. So you kind of follow the peaks, the crests and troughs of the wave. So you go, that's the sound you actually hear. That's what's called a beat pattern. And what happens is very good string instrument players, if you ever watch them get their instrument in tune, what they do is they'll actually only tune one string. And then they tune the second string to the first one. And when they hear this beat pattern, is not in tune. But when they hear a single solid sound, then you actually know it's in tune. If you ever see a real piano, not a digital piano, but a legit real piano, and you press the key, and if you watch the inside of it, you're actually going to see multiple strings being hit. For the lower sounds in the piano, 3 strings actually get hit. And what a piano tuner does is they literally pluck each string. And if they hear this beat pattern, this louder, softer, they know the 3 strings are not in tune. But when they pluck any 2 or 3 strings together and they hear one sound that is of a single amplitude, they know it's actually in tune. Because what's happened is the waves that are being produced by each string are of the same frequency. And when they're of the same frequency, the amplitude is actually going to end up being the same. And that is it for this first part. So this first part was on waves, part 2 is on sound, and part 3 is on light. So again, your assignment for this week is to basically take notes on everything I just talked to you about. So you've got the video now, because obviously you just watched it, and the notes online, the PowerPoints are online, so you can kind of follow along a little bit better. I will see you shortly.